All right, now that we've talked about what radiative forcing is, we can think about how we model radiative forcing and model the climate. When we try to model the Earth system, we have to break it up into something that a computer can handle. And that means we have to take this very, very complex system and break it down into mathematical equations based on the laws of nature. So we have mathematical equations for energy transfer, mass transfer, momentum conservation, so on and so on. And in order to apply these mathematical formulas that represent the natural laws of nature, or the fundamental laws of nature, in a computer, we have to break up the world into cubes, into a grid system. Typically, we break up the world into cubes based on latitude, longitude, and altitude. And we know that between each of these cubes, there's going to be a transfer of mass, energy, water, wind velocity, heat, things like that. So we model the transfer of these things from cube to cube to cube with mathematical expressions. Now, you can imagine each cube has 6 faces. And if we were to put a cube, at the resolution we would need to model climate all around the world, that's going to end up being thousands to millions to billions of these cubes. And each one is connected on 6 faces. So on 6 faces, there's going to be this mathematical equation, and not just one mathematical equation, but many, many, many mathematical equations that all represent the transfer of some variable, be it heat, energy, water, whatever. So this requires a tremendous amount of computing power. When we talk about climate models, this is not something that you can just run on your laptop, nor can you run it even on a very good desktop. You require a supercomputer to run these climate models. And when I say supercomputer, I'm talking about computers where a single computer takes up an entire warehouse, right? There's a picture of a supercomputer here. There's a man in the back there for scale. And this is just one small snippet. Supercomputers take up, again, warehouse worth of space. And when we use these supercomputers to run a model simulation, obviously not everybody can be running a simulation at the same time. So we have to collaborate with each other around the world to share these supercomputers. And so we will remotely use these computers. You don't actually have to go to this warehouse and type on the keyboard there. You can remotely connect and run this model from wherever you're at, as long as you have the grant funding, the agreement, the collaboration, all of that good stuff. Now, when we run these models, because we can't run everything all at once, we just don't have the computing power for that, we have to make some trade-offs, right? We have to think about the resolution in both time and space versus computational cost. There's no way that we can break the Earth up into cubes that are just, a couple microns in width, because that would take far too long to run that model. And then nobody else would be able to use the computer for perhaps years while that model is running, right? We just can't do it. Likewise, we have to think about the inclusion of climate processes. If we were to include every single process that we know about on Earth, again, it would just take far too long. We don't have that computational power to do that. So instead, we have to choose which processes are more important, which ones are we going to choose to model for this specific scenario, and so on and so on. Finally, we have to think about the number of simulations to assess uncertainties. So when we run a climate model, we don't just run it once. We run it many, many times, right? Tens of times, each time starting with a slightly different beginning scenario, right? And we do this because of these feedback loops, because of these uncertainties, because of these thresholds. We want to see, with very, very similar starting scenarios, what is the range of possible future projections? Right? And that gives us, well, what's the average, what's the most likely, but also what's best case, worst case, what is possible in the future. So ideally, we'd run these models thousands of times, but obviously we can't do that. So we have to think about, well, how many simulations would it take for us to be actually confident in our results? So typically, again, we can't model everything all at once. So we typically model individual components separately, such as just modeling the atmosphere or just modeling the ocean, first in isolation, And then we bring those various components together into a comprehensive model that undergoes systematic evaluation. And to evaluate it, right, we run it many, many times, and then we compare it to observations and make sure that our model is able to accurately represent the observations we know to be true. If it doesn't represent what we know to be true, then the model doesn't work. Okay? We also have to constrain our models. Basically, we have to say, we know at this specific time, this was the amount of effective radiative forcing, this was the temperature, this was the wind velocity at this time. So we force the model to match the observations at certain time periods. And we also don't let our models go too crazy, right? If we see it starts spiraling off, creating world temperatures of 1 billion degrees Celsius, well, that's not possible. So we have to limit it to what we know is physically possible. So there are 3 different types of models. With all of these different considerations, there are 3 different types of models that we can use. The first one is the atmosphere-ocean general circulation model. This is a very, very popular one. It's high resolution in both space and time. But because there has to be a trade-off, we can't have everything, these leave out biogeochemical feedbacks. But it includes the atmosphere, ocean circulation, land physics, and so on. Right? Now, obviously, we can't always leave out biogeochemical feedbacks. They are often important to the climate. So if we want to include those, we have to give up something else. In Earth system models, we include the biogeochemical cycles, such as the carbon cycle, the nitrogen cycle, but we have to lower the resolution, either spatially or temporally, we have to lower the resolution. Now, if we want to have both high resolution and include biogeochemical cycles, we can do that. We just have to limit the space that we're looking at. Rather than looking at the entire world, we might focus just on Georgia, right? And we call those regional climate models. So all of these do some things very well, but leave other things out because we just don't have the computational power to do everything we want at this point.